All right, so let's go ahead and launch into our lecture. Tonight we're going to be talking about graph coverage as applied to source code. So here we are on our class structure. We've got graphs. We're going to be talking specifically about source code tonight, how to make graphs out of source code, how to annotate them with source code details, and what kind of testing can we get out of doing that. So as I mentioned last week, it's pretty clear that graph criteria are often applied to source code. Generally, when we do that, we're talking about the control flow graph. Hopefully, all of you have at least a little bit of experience with control flow graphs or understanding of control flow graphs. And really, it's just a graph that is showing the possible paths of execution through the piece of software. And when we look at a control flow graph, node coverage is just requiring execution of every statement. Branch coverage or edge coverage is requiring execution of every branch. And then data flow coverage that we started talking about at the end of last week, that requires us to take the control flow graph, annotate that control flow graph with variable definitions and uses, and then use that information to come up with data-based paths through the graph. So a super quick review of control flow graph. We're using the CFG to model the execution of the software. So a node on our graph will contain a statement or a sequence of statements such that if the first statement in the sequence is executed, then all statements in the sequence are executed. So we're basically trying to maximize the amount of code that's in each node on the graph. By saying anything that's an inline sequence of code that doesn't have any control statements, that can't jump anywhere else, that can all be compressed and put in one node in the graph. And there are a couple of exceptions to doing that I'll talk about as we go on, but that's the basic idea. We're not, a node in the graph does not represent a single line of code necessarily, because then the graphs just get too large and complex for no good reason. But each node represents all of the code or all of a sequence of code that will be executed at once. And then an edge is a transfer of control or a decision. So it's an if or a loop or some other, a return, an exception throw, something like that, that's transferring control out of a linear sequence of functions. And then we can annotate that control flow graph with variable definitions or variable uses, or we can even annotate it with the source code that it represents. And we'll see a little bit of each of those tonight. So let's look at a couple of different structures, a couple of different source code structures and how they are represented in a control flow graph. So here on the left side, we have an if then else. So basically, we're coming into node 1, and then node 1 is doing a comparison of X and Y, and then it's either branching to the then or to the else. Now, one thing I want to point out here, the textbook has chosen to label decisions on graph edges rather than in graph nodes. So generally speaking, this is the approach that I'm going to take as we go through the class. I'm going to be modeling those decisions on edges rather than in nodes. So node 1 in this case ends up kind of being a dummy node, right? Because there's really nothing happening there, because this if X is less than Y is actually being represented on the edges. And then if it's true, we come down here, we execute Y equals 0 and X is X plus 1. If it's false, we come down the right side, execute X equals Y. And then at the end of that statement, we have to come back together. And if there was nothing else happening here, then that would come back together into a dummy node, or it would come back together into a node that contains whatever the lines of text or the lines of code are that come after that. So, like I said, we can notate the graphs as we've done here, putting the decisions on the edges. It's also not uncommon to see graphs that are putting the decision in the node and then labeling the edges true and false. I'm okay with either one of these. If you're asked to build a control flow graph out of a piece of source code, you can choose either approach, and that's fine. So here's an if return. So if this statement is true, if this comparison is true, then we return. Otherwise, we do something else in return. So that actually gives us two return nodes and two terminal nodes in the graph, right? There's no edge from node 2 to node 3. If this statement is true, we execute a return. That's a terminal node. And if it's false, then we skip over that, come down here and execute our print, and then a return, which is also a terminal node. So this is a very simple case of having a graph with multiple terminal nodes. And having multiple terminal or final nodes is not at all uncommon in a piece of software. You can have multiple returns or multiple exits of whatever type. It's not an uncommon approach to programming. So this is a fairly typical thing to see. Here's a while loop. So while loops are a little funny because if we really want to be picky, we have to model the while loop. We have to model the while loop carefully, and we have to have a dummy node here. So node 1 contains x equals 0, and then we enter the while loop. But there's no initialization or anything else that happens in the while loop, so I actually don't need to do anything except the test. So node 2 is a dummy node that doesn't do anything because the test is implemented, as the textbook does, on the edges beneath it. However, we still have to have node 2 because if we execute the loop, we have to have some way to come back around to the test again. So we need that node there so that we can come back around and prepare to execute the x is less than y test again. And eventually that will become false, and we'll exit that loop, drop out of it, and come to the final node that has the return statement. And again, as I mentioned earlier, we could annotate this differently. We could annotate node 2 as saying while x is less than y, and we could mark our branches true and false, and that would be equally correct. And we have a for loop. For loops actually make for a fairly complex control flow graph because we have, first of all, the initialization node, right? This is where we're initializing x to 0. We have to do that in a separate node because if we did it in the comparison node, which comes next, we'd be reinitializing x every time through the loop, which we don't want to do. So we have to have this initialization node to set x to 0. Then we have this dummy node that does the comparison, x less than y, which can either be true or false. And then we'll execute whatever content is in the loop. And then we'll have an increment node, right? This is the x plus plus, or x equals x plus 1. That's the node or the loop increment that happens. And then we jump from the increment back up to the dummy node that implements the comparison. So there are a few other representations that we could use here. So first of all, we could use, as I've said several times, we could annotate node 2 with x is less than, if x is less than y, and annotate edges 2, 3, and 2, 5 with true and false. We could also take this initialization statement, x equals 0, for compactness. If we wanted to, we could put that statement in whatever the previous node was, right? Because we don't need this node 1 to be a separate node. If there was some preceding node, we could tack the initialization on the end of that. We could also tack this loop increment statement on the end of node 3, because, right, it could be done in there. Having a node that just goes linearly to another node is topologically the same as combining those nodes. So those are different things, different representations that we could make. You will often see these broken out like I've drawn here, to just try to make it very clear what's happening with the loop. But I'll have some examples coming up later in the slides that will compact to them simply for space reasons. We've got a do loop, so do is a post test. So we have some initialization or whatever might come before the do loop. Then the do loop itself, let's see, the do loop itself, this seems wrong. Oh, okay, I'm sorry. It's correct, it's just a little bit drawn a little bit funny. This annotation should probably be over here on the right side because it's the node, it's node 2 that contains the contents of the do loop. It's not this edge, it's the node. I'll fix this after class tonight to make it a little clearer. So node 2 contains y equals f of xy and contains x equals x plus 1. And then we get to the end of the node, and as we're exiting the node, the edges represent the while case. Is x less than y? Yes. Then we'll have a self edge back up to node 2 and execute the contents of the do loop again. And if it's not true, then we'll exit the loop. So sorry for that confusion, but this content, this annotated code over here, is really associated with the node, not associated with the edge.
Professor,
Yes.
What about a recursion call? Will it go to the main node, I mean the initial node?
A recursion call. So you wouldn't normally represent recursion. You wouldn't normally represent recursion on the control flow graph. You would represent the call to itself as part of the code, right? As part of the code annotation, if you were annotating it with code, but you wouldn't represent that with a line. Because representing it with a line on the graph really isn't accurate, because really what you've done is you've spun up a whole nother control flow graph of the method that you've called. And then if you recurse again, you have a whole nother copy of the control flow graph of the method that you called recursively. And so you've got this stacking of control flow graphs would really be the way to represent it. Because otherwise, if node 2 was a recursive call and I drew it as a line up to node 1, how do I ever represent returning and getting back to node 2 again, right? You really need to represent that as a stacking of control flow graphs, and each one of those control flow graphs has its own current state as far as where the program counter is.
Okay, I understand. Thank you so much.
Mm-hmm. So control flow graphs can get pretty nasty. We've got breaks and continues here. So if we find that, let's see, break is over here on node 4. So here we are inside a loop that's nodes 2, 3, 5, 6, right? Those are representing a loop. If we execute a break in the loop, that then is a jump out of that loop to whatever comes after the loop in the code. Where a continue will just kind of skip back, it will skip away from the rest of the loop, right? So there's no edge from the continue statement to the statement that follows it. Instead, the continue statement branches back up to start the next execution of the loop. It's a kind of an ugly example. It takes a while to look at this and really understand what's, what that all really represents. And I think it's a strange enough example that I'm not going to spend a lot of time on it here in class, but it's worth taking a good look at this and making sure that you understand what it represents. I would be unlikely to throw a graph like this at you for a quiz. That would fall under my, that would be what I would consider kind of a dirty trick. So we can have switch or case statements, and they can be represented in a control flow graph. And the key interesting thing to note here is that if you have a break statement, that takes you out to the following code. But if you lack a break statement, like case N, then the control flow is different. And instead of executing case N and setting Z to 25 and then coming out of the statement to print X, we don't have that 2.5 edge. Instead, we have this 2.3 edge because that takes us right into the next case. So that would be the graph representation of having one case fall through into the next. Exceptions. Exceptions are a real pain. And in fact, in general, we would represent exceptions that we're explicitly throwing, like this code does. Generally speaking, we do not try to represent implicit exceptions. So in Java, you can have a runtime exception from all kinds of things, from a divide by zero, from an overflow. We generally would not be trying to represent them on the graph because although we technically could, and technically that's really what's happening, the graph becomes unbearably complex. So here, basically, anytime we're throwing an exception, like here in node 2, where is that throw going to go? That throw is going to go to the catch. Where's the catch? Yeah, okay. So we're going to, when we execute readline, if readline throws an IO exception, that's going to execute, that's going to branch over to the catch. The catch is going to print stack trace, then we're going to fall out of the catch, so we're going to go to the return. If we get through that readline statement, then we're down here. So now we're doing a test to see if length is greater than 96. If it is, then we're going to throw an exception, and that throw is going to take us to the node where we catch the exception and do the, this is actually wrong, it should say e.print stack trace, not e.getMessage. Slide 13. So we'll throw, the throw will be caught in the node where the catch statement is, or the throw will have an edge to the node where the catch statement is, and then that will complete its execution and come out to a return.
Sir, is the e.getMessage not used for like getting the actual message that you added on to the exception, so like too long or too short?
Yeah, we could certainly do that. This is just a mismatch between what's actually written here in the code, right? Because the code is e.print stack trace, and that's this node. So this node should be annotated with e.print stack trace, right? Or if getMessage is what we want to do, then the code should just have the matching thing, right? My point was only that there's a mismatch between the code and how the graph is annotated.
Okay, in that case, can we just go to like 2 directly from there, or no?
From 2.
So like go from like 4 to, if we're throwing the exception, we go directly to the e.print stack trace that's already there defined in number 2.
Yeah, so that's catching. This code is incomplete. This code doesn't match the graph. All right, I'm going to kick this aside because there's nowhere to catch these. This code doesn't have anywhere to catch these throws. So yeah, because this catch of the IO exception, that's going to happen. That's going to catch what happens at readline, but there is no catch for these other exceptions. Exception too long and too short. There's no catch for that. So that is either going to propagate outside of this piece of code, which is kind of hard to represent. But really, the case here is that it's missing a catch for exceptions that aren't IO exceptions. All right, so I'm going to kick this one aside, and I'll have to update this graph and correct it. Sorry about that. All right, so let's look at an example. So here we've got this compute stats function. So we give compute stats an array of integers, and it computes a number of things. It computes how many there are and what the mean and median are and what the variance and standard deviation are, and it prints all that information out at the end. So we'd like to build ourselves a control flow graph to represent this. So we can take the maximum amount of code that we have here at the beginning, right? We get called, our entry point is here at the compute stats function call. So we set length, we define some values, we set sum to 0. And in this case, just to keep the graph smaller so that I can fit it all on this page and keep it a reasonable size, I've taken this loop initialization into I equals 1, and I've added that into, I've compacted that up into node 1 instead of giving it its own initialization node. And those are functionally identical, right? Because 2 nodes with a single edge between them is the same as 1 node. So there's all of the stuff that we can put in node 1, but now we have a test coming up. So we're doing our test here in our for loop to see if I is less than 1. So if it is less than 1, we'll take this edge. If it's not less than 1, we'll take that edge. And then what happens next? Well, let's say it is less than, or I said less than 1, I meant less than length, excuse me. Let's say that comparison is true. So we'll execute the body of the loop. So we'll say sum plus equals numbers. And then I've also combined the loop increment into here because, again, I could have it in a separate called out node, and that's not uncommon, but it's functionally, it's functionally and logically equivalent to just compress those 2 nodes into 1. So we'll execute the loop, and then we'll go back up to the loop comparison. Now, if I go the other way, if that comparison, if or when that for loop comparison is false, I'll fall out of that loop. Now we've got another block of code. So we'll compute mean, we'll compute mean, we'll compute var sum, we'll initialize I to 0 again. And then we've got our next comparison in this loop. So I can be less than length, or it can be greater than equal to length. If it's less than length, then we'll compute the contents of the loop, right? We'll set var sum, we'll increment I, we'll jump back up to the comparison. And if and when that comparison statement in the for loop becomes false, we'll exit that and we'll set var and SD and all the rest of this code because that all happens in one place, and then we return. So that's a terminal node. So that's kind of how we'd go about building up our control flow graph from any particular piece of code. So let's look at what our edge coverage test requirements are now. So we can look at this graph, and by the quiz grades, I think you all got pretty good at figuring out edge coverage test requirements. So 1, 2, 2, 3, 3, 2, 2, 4, etc. And so what are some test paths that can get us there? Well, we have to start at 1. So here I'm going to take an approach of basically trying to maximize what I accomplish on my test path. So if I'm looking at this, graph, my kind of informal greedy algorithm for accumulating as many test requirements as I can, I'd say, well, wow, what happened there? All right, I'll go 1 to 2, right, because that's my only choice. And then I'll do that loop first because that'll allow me to accomplish some other test requirements. If I skip the loop, then I'm going to need another test path to come back and do the loop. So I'll just go ahead and I'll do the loop. Start at the initial node. So I'll take test path 2, 3. My animation is a little messed up in here. I apparently didn't play this through after editing it this week. So I'll take 2, 3. 2, 3 is going to take me into the loop. So that 2, 3 in my test path, that captures this 2, 3 test requirement. So like I said, little tip, take the loop first. That's going to help you maximize your coverage. Then I'll go 3-2 because that's the only thing I can do next. And that actually lets me capture another test requirement. And then from 3-2, here I am at node 2. There's no point in going back to 3 again because I've already captured 2-3. That's already in the test requirements that I've gotten with this test path. So now I'll go to 2-4 instead. And that will capture my 2-4 test requirement. From 4, I can clearly only go to 5. That captures my 4-5 test requirement. From 5, I've got a choice. I can go to 7 or I can go to 6. So following my greedy algorithm, I'll go to 6 first to try to maximize what I can accomplish here. So I'll go to 5-6. That captures 5-6. From 6, obviously, I can only go to 5. That captures the 6-5 test requirement. And then from here, I'll go to 7. That'll take me to the end of the graph. It'll end my test path and will also capture my last test requirement. All right, so here's my test path, 1, 2, 3, 2, 4, 5, 6, 5, 7, and I've captured all of the test requirements by doing that. So pretty nice. We managed to do that with one test path, so that was convenient. So what if we have edge pair test requirements? So if we have edge pair test requirements, here are our test requirements. What will our test paths look like to satisfy edge pair? Well, I'll start off with 1, 2, 3. I'm going to take my same basic approach of going around the loop. So I'll go 1, 2, 3. That's going to capture my first edge pair. Where do I go from there? Obviously, I go back to 2. So now I'm at 1, 2, 3, 2. So that captures edge pair 2, 3, 2. So from there, I'll go to, well, let's see. From there, I can go to back to 2, or back to 3, excuse me. I can go back to 3, and that's going to let me capture edge pair 3, 2, 3. Right, so what I'm doing here is I keep on adding individual nodes as I progress through the graph, and then I'm looking at the 3 last nodes or the 2 last edges and trying to figure out if those are part of, are those part of my test requirements? Or alternatively, I'm looking at the last 2 that I've covered in my test path, then looking forward into my test requirements saying, where do I want to go next? So from here, I was last at 2, now I'm at 3. Where can I go next to pick up a new test requirement? Well, 2, 3 what? Well, 2, 3, 2, I've already done that, and there are no other 2, 3s. So my next one actually, oh, I'm going the wrong way. So I have to go back to 2, 3, I have to go back to 2. So now my most recent edge pair is 2, 3, 2. And I didn't actually increase my coverage because I had captured 2, 3, 2 earlier. But it was a step that I needed to take to keep moving through the graph. So where next? If I look, I've been at 3 and I've been at 2, so 3, 2. What else is out there? There's 3, 2, 3, but I've already captured that one. No point in doing that. There's 3, 2, 4. Great, let's go to 4 next. So we'll go to 3, 2, 4, capture that test requirement, and we'll continue to just sort of work our way through, identifying each next test requirement that can be accomplished from where we are in the graph. And we'll iterate through until we get to the end. So now we've done 6, 5, 7. We've gotten to the end of the graph, but we still have 2 edge pair test requirements that haven't been satisfied yet. So that tells us we need another test path. So let's go ahead and take off on that test path. And where do we start? Well, obviously we have to start at 1. What do we want to do? Well, we want to capture our remaining edge pair test requirement. So we'll pick 1, 2, 4. And then from 1, 2, 4, We care about 457, so we'll go to 5 next. Now we have 245. 245 isn't a new test requirement. We had captured that earlier, so that doesn't add anything to us or add anything for us, but it puts us in position to capture the remaining edge pair test requirement 457 by going from here to node 7. And so with those 2 test paths, we've satisfied edge pair coverage. All right, now we can look at prime path. Because this animation is kind of broken, I'm just going to jump out of that view. And I'm going to go into this view for a little bit. I'll switch back later, but this is just going to work better because I got those animations a little messed up. All right, so if we want prime path test paths, well, first we have to identify all the prime paths in the graph. So we've got 1, 2, 3. That's a simple path. It can't be made any longer because the next thing we would do is duplicate or return to 2 and have 2 appearing twice. 1, 2, 4, 5, 6, 1, 2, 4, 5, 7, 2, 3, 2, 3, 2, 3. All right, so we've identified all our prime paths. So now let's go about our greedy approach to test path development again. I'm not going to go through step by step this time, but basically I'm taking kind of that same greedy approach. I'm trying to capture all the test requirements that I can. So I've selected 1, 2, 3, 2, 3, 2, 4, 5, 6, 5, 6, 5, 7. And that has captured as many of these prime paths as I could with a single test path. So now I need another test path to try to capture some more test requirements. So that test path could be simply 1, 2, 4, 5, 7. I have to do that, right? That's a prime path. It's also a test path, very convenient, so I can knock that one off. Then I've got 1, 2, 4, 5, 6. That's a remaining test path. So 1, 2, 4, 5, 6, 5, 7 is the test path that I need to capture the 1, 2, 4, 5, 6 prime path. And then I have a 3, 2, 4, 5, 7 prime path. And so I can capture that with a 1, 2, 3, 2, 4, 5, 7 test path. And so 4 prime paths, or excuse me, 4 test paths will satisfy all of my prime path test requirements. All right, now I can jump back into view here. Okay, so now we want to return to the topic that we talked a little bit about the end of last week, and we want to expand this a little bit. We want to look at data flow coverage. And so we introduced a couple of definitions last week, a couple of terms last week. So we have a def, and a def is a location where a value is initialized or the value is stored into memory, right? Somewhere where a variable is set. When can that happen? That can happen, obviously, when the variable appears on the left side of an assignment. So the statement x equals 44 is a def of x. We can have a def where the variable is an actual parameter to the call and the method changes its value. So anytime, you know, if a parameter is passed in, we change the value of that parameter, then that's a def of that parameter. We also have an implicit def when we have a parameter at the beginning, at the entry point of our method. There's an implicit def for any arguments or any parameters that are passed in at that point. Then we have uses, and a use is where the value of a variable is accessed or used in some way. So that can be where it appears on the right side of an assignment, or it appears in some kind of conditional test, or it's used as an actual parameter to a call, right? If I have a variable and I call some other function and pass that as a parameter, that call is a use of that variable. When I'm outputting it in a print statement or something like that, or when I'm using it in a return statement. Those are all uses of that variable. So basically, anytime I'm accessing the value of that variable without setting it, that's a use. So we talked about these definitions last week. We can have a def use pair or a DU pair. And this is a related def and a use, where starting from the def, there's some path that I could traverse where I can reach the use. Now a DU pair does not need to be def clear. And def clear means that the path from the def to the use doesn't have any other defs along the way. So a DU path then is a path from the def to the use that is def clear. So imagine that I had a def and then a def and then a use. The first def and the use, they're a DU pair, but they're not a DU path because there's another def in the middle. But that second def to the use, that's a DU pair and a DU path because it's def clear. There are no other defs along the way. So we can get some interesting cases here when we have defs and uses in the same node. And a def and a use in the same node are a DU pair only if the def comes after the use and the node is in the loop. So like this example here, we're using X and then we're defing X, and then there's a way for us to come back around and use X again. So this def leading around the loop back to the use, that is a DU pair. If it were the other way, if we deft X and then used X, then that's not a DU pair because a def and a use in the same node isn't a DU pair if the use comes after the def. So the two cases where it's not, right, where we're using it in the same node. So this second example, we're defing X and then we're using X. That's not a DU pair simply because they're in the same node. So that's called a local use, and that local use is really of no interest for testing because as long as we execute that node, we've executed the def and the use. So it's really not useful or interesting for for DU pair or for data use testing. And then here's the case. We're kind of taking our first one in the loop and we're taking away the loop. So now we have a use of X and then a def of X and no loop back again. Well, that's not a DU pair because you can't get from this def back to this use again. So a def and a use in the same node are only a DU pair if the def comes after the use and we have a way to loop back around to the use again. All right, so now loosen yourselves up. We've got a little bit of a collaborative example that we're going to go through. It's a little bit longer than I'd like, but hopefully it will be a useful scenario. All right, so we've got compute stats here again. This is the method that we looked at earlier. We've got our control flow graph. Our control flow graph is annotated with the source code. So this is the same example we were looking at earlier when we built this graph. So now let's first take this source code and let's re-annotate the graph. We're going to take the source code off the graph and we're going to annotate the graph with defs and uses. So it's hard to show both the source code and the defs and uses at the same time. So I'm just going to show you. We're just going to jump right to the defs and uses. So here in node 1, we're defing numbers, sum, length, and I. Well, let's go back and look at that. We're defing numbers because it's passed in as a parameter. So that's an implicit def. We're defing length because we've set it here. We've defed sum, we've defed I. What have we used? Well, our uses in node 1 is numbers. Let's go take a look and see why that's true. Okay, because we used numbers to determine its length to set length. So there's our use of numbers in node 1. So then edge 2.3, edge 2.3 uses I and uses length. Let's take a look why. Okay, because edge 2.3 was testing I and length to see if I was less than length. So we could go through this and we could map all of these defs and uses back to our source code. And in fact, that's exactly what I did, although the other way. I was looking at the source code saying, okay, what got defined in this node? What got used in this node? What got used on this edge? We can't have a def on an edge because there's no lines of code. There's no statements on an edge. There's just comparison values on edges. So we can't have a def on an edge, but we can have a use on an edge. All right, so now we've got all our defs and all our uses. So we'd like to build up this table of nodes and edges and document what all the defs are and what all the uses are for each node and what all the uses are for each edge. And as I said, you can't have a def on an edge, which is why that right-hand table with the edges doesn't have a defs column. So let's go ahead and start that. So we've got node 1. What are our defs in node 1?
Numbers, sum, and length.
All right, numbers, sum, and length. Great. What are our uses in node 1?
Numbers.
Numbers. Excellent. Now we'll go to node 2. What are our defs in node 2?
No defs, just
No
uses.
defs.
No defs. And also in node 2, no uses, because our uses are actually on the edges. So we'll come back to that. All right, so we could go through this, and I think you're already getting the idea. So I'm not gonna draw this out so painfully as to go through each one. But there are a couple that I want to point out here. So we go to node 4. We've got our defs. We've got our uses. Node 5. We've got no defs, no uses. Node 6. We're defing var sum and I. We're using var sum numbers I and mean. Node 7. We've got a couple of defs, we've got a bunch of uses. Great, so now we've got our defs and uses all built for our nodes. So now we're gonna go back and we're gonna look at our edges. So we can look at edge 1, 2. What uses does edge 1, 2 have?
No uses.
No uses, right. Edge 2, 3.
I length.
I and length, right, exactly. And so we can iterate through the rest of our edges. And here's the table, the def use tables that we've put together. So now we've got all of our defs and all of our uses for every node and all of our uses for every edge. So now we can look a little bit about what our criterion might be. And we talked a little bit about this last week. So now we're going to take a little bit of a deeper dive, right? Our first and our simplest data flow coverage criterion. Requires that we have in our test requirements, at least one path from each def to some use of that def, right? To some use of the variable that we defed. We can get a little more complete and go to all uses coverage, which requires us to have at least one path from each def to each related use of whatever we defed there. And so let's look first. First, we're going to put together our DU pairs. So we've got, these are our variables. Let's find where our DU pairs are. So if we go back to our tables and our variable that we're interested in is numbers, where are our DU pairs?
Where there's a def for a variable and then a use.
Yeah, so a def and then a use. So is
Like
1 a DU pair?
No.
Right, that's a local use. Great. So where would I heard 1 and something else.
1 and
1
3.
and 3.
1 and 3. 1 and 3, that looks, offhand, that looks like a DU pair. 1 and 4 looks like
1,
a DU
4.
pair.
1 and 6.
1, 4, okay, so 1, 3, 1, 4, 1, 6 looks good. 1, 3, 1, 4, 1, 6, good DU pairs. Now let's consider length. Where do we have DU pairs for length?
1, 4,
4.
1, 7.
1, 4, and 1, 7. Well, we also have some edges. So we've got, yes, 1, 4, and 1, 7, but also 1 to 2, 3, and 1 to 2, 4, and 1 to 5, 6, and 1 to 5, 7. And this is kind of a little bit kind of ugly notation, but basically we're saying this DU pair is the def is at node 1 and the use is at edge 2, 3. So it's a lot of, what's the acronym for Lisp? Lots of insignificant, silly parentheses. So we've kind of got the same thing going here. All right, what's our DU pairs for Mead?
4, 7.
4, 7.
4, 7. And for var?
No DU pair.
Yeah, it's tempting to say 7, 7. However, if we actually went and looked at the code, we'd see, well, okay, we defed it, and then we used it in the same node, so that's a local use. That's not a def. Great, and we could iterate through the rest of these, and I think it really sounds like you're getting the hang of it. So we'll zip through SD and mean and sum. And so now we've put together our table of all of our DU pairs for the compute stats function. So now we'd like to turn those DU pairs into some DU paths. And then eventually we're going to turn DU paths into test paths. So here we had numbers, we have DU pairs of 1, 3, 1, 4, 1, 6. So what are the related DU paths for these DU pairs?
1, 3.
So 1, 3 is a pair, it's not a path, because
1,
there's
2,
no
3.
edge from 1 to 3.
1, 2, 3.
1, 2, 3.
1, 2, 3, right. How about the DU pair of 1, 4?
That doesn't work because then 1,
1, 2,
1,
4.
2, 3 is a subpath of that, right?
So we don't really care about any subpaths right now. We're just taking our DU pairs and trying to find DU paths. And a DU path is a def clear, right? A def clear path from the def of some variable to its use.
I think it's 1, 2, 4.
1 to 4.
1, 2, 4.
Yeah,
1, 2, 4. All right, how about 1 to 6?
1, 2, 4, 5, 6.
1, 2, 4, 5, 6. Great. Good DU paths. Let's do another one. So we've gotten for length now, we've got from node 1 to edge 2, 3. What's our DU path?
1, 2, 3.
1, 2, 3.
Exactly. You just take that edge, you expand it into both the nodes. Both those nodes have to appear in the DU path. Great. All right. How about from 1 to 2, 4?
1 to
1
4.
to 4.
1, 2, 4. And how about node 1 to node 4?
1 to
1
4.
to 4.
Same thing. And 1 to 5, 6.
1, 2, 4, 5,
5,
6.
6.
1, 2, 4, 5, 6. Then 1, 2, 4, 5, 7. Right. And then 1, 2, 4, 5, 7 again. So there are our DU paths. Great. So for Mead, we've got 4 to 7, so that's going to be pretty obvious, right? 4, 5, 7. I don't think there are too many other interesting ones along here, so let's just kind of go forward through here since you're, clearly getting how this works. I's got a lot of them. So 1 to 2, 3, that's easy. 1 to 2, 4, that's easy. 1 to 3 is easy. And so we can kind of continue down here find all our little DU paths. So now we've got our table built up. We've got the variables, we've got the DU pairs, we've got associated DU paths. So this is interesting because we have 31 DU paths here, but only 10 of them are unique. So we had lots and lots of things to do with DU pairs. But when we worked them out to be DU paths, there's a lot of overlap now, right? Because the DU pairs, for example, we had a DU path for numbers of 1, 2, 3, but that was also needed for sum, and it was needed for length, and it was needed for I, right? So we're getting a lot of reuse out of these paths. So only 10 unique paths come out of there. Now these paths are kind of interesting because we've got 3 paths that don't execute a loop. And we've got 5 paths that execute a loop at least once. And then we've got 2 paths that execute a loop at least twice. So we're starting to see, okay, I'm seeing how these paths are coming together. When I was doing DU pairs, I was starting to think, wow, that's going to require an awful lot of tests. But now that they've simplified down to just 10 DU paths, doesn't seem quite so hard anymore. So for all defs coverage, we have to cover at least 1 DU path from each def of each variable. And so I have highlighted here a selection of DU paths that would satisfy all defs, right? So really, I just need from every def to some use. So for numbers, I could have picked any one of these DU paths because they all take me from a def to some use. And for length, I could have picked any one of these. For mean, I could have picked any one of them. For sum, now I need to pick 2 because I have a def at 1 and a def at 3. So I can pick either of the ones from 1 and either of the ones from 3. Likewise for var sum, there's a def at 4 and a def at 6. So I have to pick at least 2. And then I has a lot of defs, right? I's got 4 defs, so I need at least 4 paths because I have to start at each def and go to some use. Now, if I'm clever, I'll be kind of looking ahead a little bit and trying to figure out what are my optimum choices. So if I pick 1, 2, 3, wow, I can use 1, 2, 3 in a lot of places. That's a good one to pick. Now, it actually turns out if I picked 1, 2, 4, I can use 1, 2, 4 in an equal number of places. But I should be looking for things that I can reuse, right? So I've picked 4, 5, 7 here. 4, 5, 7 gets reuse for var sum and for I. So that's nice. I'm just trying to pick my paths smartly so that I get as many as much reuse as I can. So now if I wanted to look at all uses coverage, I have to go from each def to each use. Now in this graph, that's the same as all DU paths because there are no options in the graph basically. I have to go from 1 to 3, I have to go from 1 to 4, I have to go from 1 to 5, I have to go from 1 to 6, I have to go from 1 to 7. When I say no options in the graph, what I mean is there's only one way to get from 1 to 7. I don't have multiple choices. All right, so finally now we've got DU paths. Let's convert those DU paths to test paths. And this will be interesting. So here we've got our code, our abstract syntax tree, or our control flow graph, excuse me. It's back to being annotated with source code again. I've color coded it so that you can easily match which node and which edge is going to which piece of code. And so now we want to execute DU path 1, 2, 3. What is a test path that will let us do that?
One, 2, 3, 2, 4, 5, 7.
1, 2, 3, 2, 4, 5, 7. That seems like a great test path. And what are some test input numbers that'll get me there?
There aren't any.
There aren't any. Right, that's actually an infeasible path. Why is it an infeasible path?
Because if you
No, go ahead.
execute the first loop, you have to execute the second loop because they have the same requirement.
Yeah, exactly. These loops are coupled, right? They're not independent loops. They are coupled together based on the same loop conditions. So I can't execute the first loop and not execute the second one, and I can't skip the first one and execute the second one. So this was not a feasible test path, but I can fix it easily enough. You know, the 1, 2, 3, okay, that was what we're trying to get. So I'll take the 1, 2, 3, 2, 4, 5, but I can't go to 7, I have to go through 6 first. And so if I'm gonna go 1, 2, 3, 2, 4, 5, 6, 5, 7, that's once around each loop. What are some test inputs that'll get me there?
Any number.
Yeah, really any number, right? I just have to have some number, one number in my test inputs. My array has to, my input array has to consist of one number, and that'll get me once around each loop. Great. So we can work our way through that, and I don't think I'll belabor that too badly because I know we want to get to a break and then exercises. But it's interesting that that one test path, 1, 2, 3, 2, 4, 5, 6, 5, 7, that actually satisfies a number of different DU paths. So I got a lot of, I actually knocked off a number of different DU path test requirements with that single test path. So that's nice. That gives us a limited number of other things that we need to look at. So my next remaining one is 1, 2, 4. So if I wanted to go to 1, 2, 4, I could perhaps go 1, 2, 4, 5, 7. We've already learned I can't go 1, 2, 4, 5, 6, 5, 7 because the loops are coupled, but 1, 2, 4, 5, 7, that'll get me there. And some test inputs that will accomplish that would be an empty array, right? The array has no elements. We won't execute we'll execute each loop 0 number of times, and that'll take me down that 1, 2, 4, 5, 7 path. Turns out that test actually finds a fault here in the software, because if trying to find the median number, the way this is written, if length is 0, then it'll be looking at numbers 0, right? Numbers indexed by 0, which means the first element of numbers, but there are no elements of numbers, so we'll actually get an out of bounds array exception. So we've actually got a good test that found a pretty subtle bug in this piece of software. And if we go back to look at where we what that satisfied, well, it satisfied 1, 2, 4, and it also satisfied 2 others. So again, I had one test path that satisfied several different DU path requirements. So next we'll look at 1, 2, 4, 5, 6. So if we look at 1, 2, 4, 5, 6, well, we'd like to go 1, 2, 4, 5, 6, 5, 7, but for the same reasons we talked about earlier, that's an infeasible test. I can't skip the first loop and execute the second loop. And so there's actually, in this case, nothing I can do to fix this DU path, right? I can't execute this DU path. I can't change my test path in such a way to satisfy the DU path. This DU path is just completely infeasible. So we're just going to throw that away. That leaves me with a couple more, 3, 2, 3, and 6, 5, 6. So if we look at 3, 2, 3, that's going to require me to execute the loop twice. And we've already learned abundantly by now that if I execute the first loop twice, I have to execute the second loop twice. So 1, 2, 3, 2, 3, 2, 4, 5, 6, 5, 6, 5, 7. It's a little tedious to say that. And what will let me execute the loop twice? Well, basically any input array that has 2 values to it. So that satisfies 3, 2, 3, and I bet you can see this coming. but it satisfies 656 as well. So we've now satisfied all of our DU paths by 3 relatively simple tests: a 0-length array, a single-length array, and a 2-element array, or a
Couldn't
single-element array and a 2-element array.
Couldn't we use the 2-element array and satisfy all the tests that have the 1-element array as well, and get it down to 2 tests?
No, I don't think we can. Well, wait, maybe we can, because let's see, what did we satisfy with that? 1, 2, 3. Well, we're pretty sure we can get 1, 2, 3. Yep. And we satisfied 4, 5, 7, and 4, 5, 7 is not in that multi-use test path. Oh, I'm sorry, 4, 5, 7 was the 0-element array. My mistake. It was 4, 5, 6 that was in the 1-element array. That is in the 2-element array. And then 3, 2, 4, and that is also in the multi-element array. Yes, so we could compress that further and say everything that's satisfied by the 1-element test is also satisfied by the 2-element test, so I don't really need the 1-element test. And in this case for this graph, yep, that works out that way. Does it always work out that way? Can you always satisfy all of the DU requirements from one test, from one loop with multiple loops?
No, I wouldn't think so.
I'm thinking probably not. I'm not willing to go out, again, without a lot of thought, I'm not willing to go out on a loop and say yes, because I've got this. While I don't have a counterexample in mind, I've got a nagging suspicion that I could come up with one.
Something with some if-else loops or switch case inside of the loop.
If loops are not coupled, I don't think it will work.
Well, if the loops are not coupled, yeah, then this would actually break a couple of different things. So yeah, I'm not sure that it's good as a general rule. All right, so that takes us to the end of lecture time. It's 17 after. Let's come on back at 6:25, 8 minutes from now, and then we'll jump into our exercise.